it is always stimulating, intellectually speaking, to think how things happen in other conditions. At the bottom of the ocean, at the top of a tall mountain, or in the moon or Mars. For example, the moon doesn't have an atmosphere, and there is no water, or so we think. And so how did the lunar regolith, that soil that is on top of the lunar surface, how did it form? Well, the moon is subjected to lots of radiation that eventually breaks down the rocks. Furthermore, in the absence of an atmosphere, all that dust that is floating in outer space eventually gets to the surface without burning, and so these micrometeorites, which are gravitationally attracted, remain on the surface, are able to hit the surface of the moon. Furthermore, the moon experiences thermal oscillations between minus 150 to 120 or 130 degrees, so it experiences thermal oscillations which are in the order of 250 degrees Celsius per day because of the absence of an atmosphere without any thermal inertia. So that means that the surface of the moon, the rock on the surface of the moon, is continuously being contracted and expanded, and any differences in thermal expansion, different mineralogies, etc., creates huge stresses that breaks it down. On Mars, however, all explorations were targeting to see if they could identify clays. Why? Because, as we said earlier, feldspars become clay by hydrolysis, by capturing the OHs in water. That means that there was water. And indeed, they have found plenty of clays on the surface of Mars. That means that there was water. And if there was water, because the bulk of our body, 90-some%, is water, that means that there was a possibility for life. And there you see the link between clays and life, and there may be other possibilities about the formation of the DNA as well. Part 2. We started with the rocks, now we're going to break them down. And these are the weathering agents. It could be physical, chemical, biological, and we know very well that we have been a force altering nature with our machinery and our ability to break rocks. So if we explore the physical and mechanical processes, we recognize that wind can create beautiful sculptures in desertic regions. The same can water carve very lovely shapes along the river paths. So erosion by wind, by water, is very important, also by ice. During the last glaciation, the thick sheets of ice were able to carve deep trenches. For example, the Finger Lakes in upstate New York, which look like fingers, where Ithaca is, Cornell University, they were carved the last 20,000 years by these very thick layers of ice coming north to south. So erosion is an important process. Then there is abrasion between grains. Abrasion is also important because it controls the shape of grains. At the beginning, they may be quite angular, but after multiple collisions and abrasion, they become incrementally rounder as they age. Now, thermal processes can happen in many different ways. For example, here on Earth, we may see thermal oscillations between winter and summer, the seasonal oscillations, which may be in the order of 80 degrees Celsius. Imagine all the expansion and contraction that takes place in rocks and differential thermal expansion between different grades of different mineralogy, eventually breaking down bonds. The other thermal effect that is very important is freeze-thaw cycles. which even Native Americans knew how to handle very well, where water accumulates in a groove, freezes overnight, and it creates a very large pressure, the crystallization pressure, that can split rocks apart. And it happens all the time in nature. And of course, if we see some of the beautiful ruins from the Mayas and the Incas, etc., and we go and explore, you can see the roots growing between them, and you see the power of the roots, the pressure of the roots, that swelling pressure of osmotic nature that can create significant damage and break rocks. Some of the most common processes, however, are chemical. And the typical chemical process is dissolution, where rocks, like certain pH and certain conditions, and so it will tend to dissolve until the water solution reaches the saturation condition. So you can put some salt in water, but if you put too much, there will be some salt at the bottom that doesn't get to dissolve because the water has reached the saturation condition. The saturation condition varies with the mineralogy, so dissolution is more effective in some mineralogies than others. Now, if we see the formation of clays, that's a very important point here. It is really a process of hydrolysis. If some of the videos we talk about clays, and they have OH, hydroxyls. And so if you start with feldspars, you need to add OH groups for them to become clays. And that is the process of hydrolysis. So water, the OH is coming from water, water must be involved in the formation of clays. Oxidation, that is typically the case when materials contain iron. Hydration, for example, anhydrite, which is calcium sulfate, is hydrated to become gypsum with the addition of 2 water molecules. Now imagine a calcium sulfate molecule with 2 additional molecules. It must really experience a significant expansion, and so in fact it does, which is a process of weathering and breaking rocks, but it's also causing very significant swelling pressures if you put a foundation or a tunnel, a bridge on top of anhydrite, and you expose it to the possibility of becoming hydrated. And carbonation is nature capturing the CO2 from the atmosphere, for example in water, making water acidic and promoting chemical dissolution. Biological processes are very important. They are subtle, but they play a critical role in mediating chemical reactions. Certain chemical reactions that would be very slow or would have a barrier, an energy barrier to happen, the presence of microorganisms can help reduce that barrier and allow for chemical reactions to take place. So they are really supporting, creating biomediated chemical reactions, making them possible under certain pressure and temperature conditions that otherwise wouldn't happen. And of course, we have already mentioned humans and blasting and crushing, weathering, breaking down rocks. We started with rocks, we weathered the rocks, we are ready to form soils. So the first type of soils that we can encounter are residual soils. And that means that they were not transported. So let's consider a few cases. The first one is that the rock is exposed and weathering takes place, and as it does, the upper layers are going to be the ones that are going to be weathered the most, eventually progressing to less and less weather conditions until we get to the bedrock, the intact rock. Examples, we have the Georgia red clays here in Georgia, and lateritic formations in tropical weather, soils in tropical weather, like, for example, all around Brazil. The other one is a little bit more strange, that dissolution, that weathering may be selective. So let me give it a title, Selective Dissolution, and I'm going to take it to an extreme. Remember, we were talking about evaporite formation, that sometimes they were interbedded the layers of silts and sands, which could be of volcanic origin or silicates, carbonates. Well, when eventually the salt layers get flooded with the ocean because the Atlantic Ocean formed, the Red Sea opened up, or Brazil moved away from Africa, you must wonder how come those salt layers have not dissolved, or the ones in the Great Lakes. Great Lakes is fresh water. So 700 meters down, you have the salt layers which appear not to be dissolving. And one of the mechanisms is that when the salt layers get formed, then sediments accumulated on top, and that prevented them or slowed down further dissolution. But furthermore, the salt itself, these were the sand grains that were trapped, or the silt grains that were trapped in the matrix of salt. The salt dissolved and the grains remained and repacked, creating a self-armoring layer. So now further dissolution means that the diffusion will have to take place through the self-armoring layer, and diffusion time increases with the thickness of this layer by the square, so eventually it becomes slower and slower and slower, resulting in fairly stable formations. By the way, self-armoring, we have observed it in the bottom of the Red Sea and is on top of any salt layer that we have described earlier. Now let's take another example, which is there is a volcanic eruption. The first part of the volcanic eruption, when it makes this cloud of dust, is volcanic ash. It goes pretty high up. It may even hit the jet stream. It gets transported, and then it falls down and creates a volcanic ash layer on the ground. That volcanic ash layer is fairly active. This is amorphous silica, and within a matter of a few thousand years, let's say 10,000 years, this has completely dissolved and re-precipitated. Please imagine that you have a jar full of marbles, and that these marbles are dissolving and re-precipitating onto new mineral species, from amorphous silica to clays, non-crystalline alophanes, halosites, immogolites. There are little spheres or nanotubes. Eventually, if you wait long enough, they may become kaolins and smectites, well crystallized. But currently, for example, in the area of Manizales in Colombia, this is what you encounter. So each of these grains of volcanic ash eventually gets dissolved and re-precipitates, and crystals begin forming, and while the grains itself is shrinking. What a complex formation. And then you have to wonder what is the meaning of the horizontal state of stress, not in the original jar filled with marbles, but when these marbles have dissolved and re-precipitated into new species. So this is taking place, dissolution within the sediment column. Notice this is a hybrid. Originally, the volcanic ash was transported, wind transported, and then it falls off, and the dissolution re-precipitation process takes place. Whenever that happens, they tend to be very fertile areas. This is where all coffees and bananas are coming from Colombia. I would like to finish this part of dissolution and re-precipitation with one more example. Imagine that we have a pool in a water body. This is filled with water. These are deep pools, and so fluids infiltrate into the subsurface. They get very hot, and then as they get hot, they will rise to the surface again, but now with temperature they are more effective at dissolving rocks, and so they come to the surface loaded with minerals, and they enter this water body, which is colder, and they form these pools of dense water at the bottom. Different minerals encounter other reactants, and they precipitate, forming grains within the water column. These tend to be some of the most strange soils you will encounter. Rocks, weather. If the products of weathering remain in situ, they are residual soils. If they are transported, the name of the soils will depend on the transportation agent. And remember that there are hybrids, such as volcanic ash gets transported thousands of kilometers from Iceland to shutting off the airspace in Europe. And then it settles, and after it settles, then it may become a weather soil, so transported and residual. But now let's focus on the transportation agents. And depending on their energy, they will be able to carry different size of particles for different distances. So the simplest one is just by gravity. Pieces of rock fall down, maybe under dry conditions, under wet conditions, but these are called colluvium. And if it is under dry conditions, there is an interesting sorting that takes place. The larger particles have more momentum, and sometimes they roll out further out. So the sorting is falling smaller particles nearby and larger particles further away. Ice is really a very powerful transportation agent. We saw before that it was able to carve these big grooves that became the Finger Lakes, but also as it was pushing like a big bulldozer, 3-4 kilometers thick, then by the time it ended and it began receding, it left all the material that it pushed at the end, and that becomes a terminal moraine. So if you look at the shape of Long Island, you will realize how the bulldozer came and left all the components, and Long Island is, for the most part, a terminal moraine, which means that you will find lots of sand, but huge boulders, probably the size of a room, all of a sudden in the same formation. Quite heterogeneous because ice is such a powerful transportation agent that doesn't discriminate. Water, on the other hand, has lots of energies near the source in the mountains, and it can carry large boulders. As it approaches the valleys and it loses velocity, loses energy, and it carries smaller and smaller particles, so it begins dropping the load as it moves along. And that is the sorting that you will see along rivers from the mountains all the way to the ocean. Along the way, there may be lakes. And so when a river approaches a lake, it has a certain flow rate Q, which is area times velocity. As it approaches the lake, the area across the lake is much larger. Therefore, to maintain the same flow rate, the velocity decreases. The velocity decreases, the carrying capacity decreases, and we see sedimentation taking place in lakes. If you are in some glacial lakes in the northern part of the US, you will see the layers that got formed by the winter deposition, where the water is really very quiescent and even small clay particles can fall, and the deposition that comes during the spring when there is lots of water coming out from melting, carrying larger particles, coarser particles. And now you see these layers that oscillate between winter and summer, and they form varved clays, varves. And of course, if something is layered like that, the properties are going to be very anisotropic: permeability, strength, stiffness, etc. Now, at the end of the river's carrying capacity, basically fine silts and clays remain, and those are very sensitive not only to their self-weight, their buoyant weight that them to sediment, they are also now very sensitive to electrical interactions, like dust gets stuck onto a furniture. And so these electrical interactions change when this water loaded with sediments hit the ocean, where there is high ionic concentration. And that leads to the formation of deltas, these amazing deltas that we see, the Orinoco River, the Amazon, the Nile, Yangtze River in China, Krishna Godavari in India. These are amazing delta formations with very unique properties where there may be accelerated oxidation of some products which may create very low pH conditions which are very detrimental for species in the area. Finally, we also have the wind as a very powerful transportation agent. We mentioned the volcanic ash from Iceland to across Europe, but that has also been the case from volcanoes in the Rocky Mountains and the prairies in the US, or in the Andes and the Pampas in Argentina, carrying fines for thousands of kilometers across the Sahara into the Red Sea and beyond, and sometimes from the Sahara to the US. Dunes then are quite sorted because the wind is very selective. It cannot carry an apple-sized piece of rock. And so dunes tend to have, for example, a grain size distribution typically passing sieve 40, retaining sieve 140. They are quite sorted. They have moved so many times with abrasion and collisions that they become smooth and rounded, and therefore they are not great materials for making Portland cement concrete. Finally, there is this wind-blown soil called loess, and we find it throughout Europe, Russia, large quantities in China, the central part of the US, Kansas, Nebraska, where I grew up in Cordoba, Argentina, and this loess creates such an open structure. There are silts and clays with some carbonation, adding some cementation between particles, which creates fairly metastable fabrics, so that when they get wet, they may collapse under their own weight. And you would be surprised that a house may appear 30, 40, 1 meter down, lower, in just a matter of weeks because of leakage of a pipe and the collapse of the foundation. The last part of this presentation on soil formation, which is just an introduction to show you how exciting it is and how important it is to explore two other processes. One is biogenic. I have to admit that I didn't pay enough attention in the early stages of my career to biogenic formation. However, I began encountering evidence of biogenic grains around the world, from Mexico City soils to Bogota clays, from Ariake clays to Ullum Basin in South Korea to the Red Sea. And one thing we notice is that every time soils contained biogenic generated grains, which are going to be diatoms and foraminifera, the soil properties were very unique. And so I invite you to please go ahead and look in the internet for diatoms and see the beauty of diatoms, and the same as foraminifera. These are essentially silicates, and these are carbonates. Diatoms are found everywhere, from lacustrine formations to offshore. Foraminifera is primarily in the ocean. Because of their unique geometry full of holes, diatoms have very high internal porosity. Now, when you make a mixture of diatoms and foraminifera, then all of a sudden you have very high void ratio, but you touch it and you see that it has formed a fairly solid skeleton. So they're very misleading. They give you the idea of a high liquid limit. However, when you run the plastic limit, there is also water inside in both cases, so you subtract to get the plastic index, you realize that you have a soil with very high liquid limit but low plasticity index. And that was the main concern that Casagrande had in the chart. or one of the main concerns in the Casagrande chart from the 30s and the 40s. If you go back and see the original sketches, there is a whole region there which talks about diatomaceous soils. Keep an eye on them. Take a look. You have to use basically scanning electron microscope to observe them. But it tells you that there was a very active biological system taking place, and sometimes it's not just a few mixed in the soil matrix, but actually it could be a full layer, which is what is called diatomaceous earth. The final component that has become now more and more of a challenge for engineering is the byproduct of coal combustion, called fly ash. Fly ash is the product that when coal gets burned, certain minerals form melted droplets, and because they are molten, the surface tension makes them little spheres. Now, there is lots of gas in coal that gets trapped, and so it inflates these little spheres, and these tend to be hollow spheres, depending on the temperature, depending on the mineralogical composition of the coal, and those are called cenospheres. Once again, I invite you to take a look at scanning electron microscopy images of fly ash, search for cenospheres with X, and you will see how beautiful they are. They tend to be very spherical, and you have to wonder, how is this material of these beautifully spherical particles going to behave? And we have had several failures related to fly ash, and there are many retention ponds that have fly ash around the world, which may cause issues with instability. A major failure here in the US was in the Kingston plant. The other industrial product is mine tailings. We crush huge amounts of rock to extract minerals and metals, gold to copper, or rare earth. Now, we only extract maybe less than 1%. So the rest of the material has to go back, and these are called mine tailings. In both cases, we have taken the original material out of equilibrium, and they may have a tendency for early diagenesis. This means that they may develop some early cementation so that when new layers come on top, they don't consolidate, they don't self-compact as we would have expected otherwise, or when we run a test in the laboratory. This creates a very collapsible structure, metastable structure, that may lead us to surprises. In this case of the mine tailings, please go back and look at the videos from the Brumadinho failure in Brazil. Both of them, the Kingston failure, the Brumadinho failure, give us a sense of humbleness as we approach the challenges related to industrial products. So, as the last exercise for this meeting, let me highlight that the summary that I presented today pretty much reflected my own experience exploring different soils. But it's a partial view. So let me invite you to explore a soil of your special interest. Maybe the place where you grew up or where you are a practicing engineer today. Explore it in depth. Understand the underlying processes that led to its formation, because when you do so, you will be able to anticipate its properties.